All right, class, welcome to Learning Outcome 17 video on the PowerPoint from Math 2015. In this outcome, we're going to extend our base 10 addition and subtraction to correctly model polynomial addition and subtraction using manipulatives, pictorial representations, verbal descriptions, and variable expressions. So we're going to essentially add and subtract polynomials using our drawings and using our algebra tiles. So what you need to do is you need to create a set of algebra tiles for this one according to the directions that were given in the email. First of all, how do we define addition? Okay. What is addition? Well, addition is combining like objects to produce a sum. Subtraction is takeaway, finding the difference, taking one quantity away and comparing two quantities additively. And it's also the inverse of addition. Okay, so we're just going to focus on takeaway for our lesson here. So we're going to add and subtract polynomials. Recall the algebra tiles that we have for our class. Here is a set of algebra tiles in the shape of a flower or a tree or something. Let us recall what the value of each type, coming from the top to bottom and from left to right. This is going to be minus x squared. This one is going to be x squared. Okay, I'm going to label these. Okay, so we have a total of, let's keep the categories here. X squareds, there's 2 of those. Negative x squared, there's 2 of those. And what we have for our next is x. How many x tiles are there? We have 2 here. Okay, so there's 2 of those. Just they're green sticks. Okay, negative x squared is the red ones. Okay, so it's negative x squared, negative x squared, negative x squared. Okay. They're all around here. And I think that's all of them. So we have 1, 2, 3, 4, 5, 6, 7, 8. There's 8 of those. And we have next is our single units, positive. So there's 1, 2, 3, 4, 5, 6. 6 of those. And then negative 1. 1, 2, 3, 4, 5, 6. 6 of those. So in all, we have 2x squareds. Oops. Yeah, minus 2x squareds plus x plus 2x minus 8x squared plus 6 minus 6. Okay, so we can simplify here. These will simplify. They're gone. Those are opposite. They'll be gone. We just have 2x and minus 8x squared. I meant to make these x's here. 2x minus 8x. There's going to be negative 6 x's. And when you're all said and done, 6 sticks. Okay, so now it's your turn to create your own 2D image and shape with the algebra tiles and find the total area. Okay, this is model work with the tiles. Go ahead and show you how to work with algebra tiles to model these 2 problems. We have an addition problem with polynomials, and we have a subtraction problem with polynomials. Okay? All right, class, we have this problem that we're modeling. It is 2x squared plus 3x plus 1. That's the first quantity, and that's why it's in parentheses. The first number or polynomial that I'm going to add. So I modeled them with these two blue blocks, blue squares here. That means those two are the 2x squareds. Okay, so notice that they're squares. The next part of the polynomial is 3x, so I've modeled it with these three green x-length sticks, or rods, if you will. And then I'm going to add that to, combine it with negative 3x squared, negative 4x, and positive 3. Okay, notice that the subtraction is similar to the negative numbers. So here's my negative 3x squared. So I have 3x squareds here, but they're on the red side because they're negative. And I'm going to subtract 4x, or I'm going to add that to the negative 4x right here. So there's 4 of these little sticks, or rods, that are x length. And they're red because they're negative. Now this one right here is positive 3, so I put 3 little cubes there, little squares there. Okay, so those were the algebra tiles. I've modeled my problem, my addition problem, and I'm going to combine them together because addition is combining, and the things that combine are like each other. Okay, notice that symbolically we have 2x squared here and negative 3x squared here. Those ones can combine together because they're like each other. Notice that they're both squares. Okay. For example, I'm not going to be able to combine the 3x and the negative 3x squared here because they're different shapes. Okay. And thus on the paper they're different. Even though they have x as the variable, notice that the x is to the first power for 3x and is to the second power for negative 3x squared. Pictorially we can see that difference a lot better than with the numbers. Okay, so combining things together is like the chips, the red and yellow chips, where if you have a red chip and a yellow chip, you combine them together and they will make a zero pair. Okay, so the negative 1 chip and the positive 1 chip combine together to make 0 pair. And what we can do is we do that with each piece. Okay, notice that we have like little single units here. We have little sticks, x long, and these ones were the x squared, and these ones were also x squared. So x squareds I can combine together. Okay, so when we combine them together, they will become a 0 pair. This positive x squared and this negative x squared combine together. Okay, they become a 0 pair, and then they can become removed from the board. Okay, combining another 0 pair, a positive x squared and a negative x squared, they combine together, and they'll come off the board. Now all I have left for that denomination of x squared is 1 negative x squared here. Okay, so that one will have to come and stay. Next we're going to combine the x's, the x sticks here. 1 positive x, 1 negative x will combine to make a 0 pair, and thus can be removed from the board. Same thing with these ones here. Combine together, make a 0 pair, and are removed. When you combine these two together, they become a 0 pair and are removed. Notice that there are no more x bars or x length sticks there to combine, and so that means our overall sum will be we'll have at least a negative x squared and a negative x in it. Looks like I've lost my 1. Yep. Okay, so from the units we have 1 from my first number, and I have 3 from my next number. Now they're not positive or negative pairs, they just combine together to make 4 units. Okay, so in the end I have x squared, negative x squared I mean, minus x plus 4. Okay, pictorially this is what we have. Symbolically this is what we have. So when we combine them together, we get negative x squared minus x plus 4. Okay, and that's our answer. For this problem, we're going to model 2x squared plus 3x plus 1 subtract negative 3x squared minus 4x plus 3. Now with subtraction from 2010, we know that that's takeaway. Okay? We're going to model our first number, and we're going to take away the negative 3x squared, the 4x, and 3. So we're not modeling both numbers. We're just going to model the first one and take away the parts that we need. The first number is already modeled here with our algebra tiles. We have 2x squareds here that are positive. We have a positive 3x here that they're green, which means they're positive. We have our plus 1 here. When we want to take something away, we need to, with these, just like with the chips, we need to model the parts that we want to take away. So I need to somehow show 3x squared, negative 3x squareds, and then take those away. Now if you want to introduce a negative number, I need to introduce it with the 0 pair. Notice that I don't have 3x squareds yet to take away, negative 3x squareds that is. So I only have positive x squareds, but I can't take away negative x squared or 3x squareds if they're not there. So to introduce a negative x squared, I'm going to put in a two x squareds here that are 0 pair, a positive x squared and a negative x squared. Okay? This does not change the value at all, but it does give me a negative x squared to take away. But I need to take away 3 negative x squareds. So I have one introduced there. I'm going to introduce another 0 pair here. I'm going to introduce another 0 pair here to have 3 negative x squareds to take away. Okay. Alright, so there's my 3 negative x squareds I can take away. But I want to take away them all at once, and so let's go ahead and focus on the next term, our minus 4x. Our x's, we need to subtract, we need to take away negative 4 of them, but I only have 3 positives to take away. But that doesn't make sense, so we need to introduce negative x squareds. So to introduce them into our system, we need to do it by 0 pairs. We're going to take a positive x squared, x, and a negative x in this form, and introduce them. Okay. Positive x and negative x, so I can take them away. I need to take away 4 of them, so I'm going to introduce 4 positive x's and 4 negative x's so that we can take them away. Okay, so those are all 0 pairs there. Alright, so we have all of our 0 pairs introduced, where eventually I'll take them away. The next number here is minus 3, plus minus a positive 3. So in order to take away positive 3 little squares, I have just one here, and I can take that one away if I want, but I need 2 more. Okay, so to introduce 2 more positives, I'm going to introduce a 0 pair of little squares and another 0 pair of little squares. Once I introduce only 2, that's sufficient to take away 3 of them. Okay. Now I can go ahead and take away. I'm going to take away my negative 3x squareds. That means they're off the board. I'm going to take away my 4x's. I'm going to scoot these guys over. And then take away the 4x's. So there's 1, 2, 3, 4. They're taken away now. Off the board. Scoot that guy closer. Now I need to take away 3 positives. I'll take away 1 from here. Positive units. 2 from there. 3 from there. And end up with the negative 2 units here. Alright. So here we're at now we need to do an exercise like we did before, which is just count what we have left. We have 1, 2, 3, 4, 5 x's squareds. Okay, so when I modeled them, I took all the appropriate pieces away. Now I have 5 positive x squareds left. I have 1, 2, 3, 4, 5, 6, 7 x's, and 2 negative units, minus 2. Okay, so 2x squared plus 3x plus 1, subtract a negative 3x squared minus 4x plus 3 is the same as, or equal to, 5x squared plus 7x minus 2. Okay, So which one of these are like terms? We're going to go ahead and move to the topic of like terms. Now, in order to add them together, they have to be like enough to each other, meaning that they have to have the same variables to the same powers. Okay, and it doesn't matter if they switch around or not, like if there's x times y or y times x. Those are the same variables. So let's go ahead and take a look at this list of expressions or terms and which ones are like enough that you can add them together, that you can combine them. So for xy, we need to find out another one that has xy in it. And looks like we have one right here, xy, even though it's not in that order. Okay. So here's our first pair. Defend that these are like things from a picture. Okay, so we have room for a picture here. I have 4 xy's. Now, recall that this little cube is equal to 1. This stick is equal to x. And this square is equal to x squared. Okay? We haven't encountered anything with xy in it yet. But what would it be? The letter x is just a variable, a certain number of ones stacked together. Now if we have y is another stack, but different in size. So we do smaller stacks with y. Then that means that y squared is going to equal a smaller square than my x squared. And we also have xy. Okay, xy is a rectangle where one dimension is x, one's y being the shorter one in this case. Okay. So it's a rectangle. Now if I have 4 xy rectangles, let's take a look and see if we can combine them. Okay, I have 4 of them. So this is going to be y and this is going to be x. The lengths. Okay, can we combine them with 3 yx's? Now yx would denote a different orientation. Okay, so we have 3 of those. Now, are they the same object? Well, all we have to do is orient them. And we have our xy rectangles. Rotate them. Okay. So those are now rotated and they can combine together. So 4xy plus 3yx. How many xy rectangles do I have, or yx rectangles? We have 7 xy's. Okay. They can combine together because the yx thing. Okay. The numbers in front are just coefficients and they tell you how many you have. Okay. And those are all positive. Okay, so what we have here is more like terms. Got to find more like terms. We found 2 already. And it looks like the second one is 0.7 x times y squared. Now they have to have the same variables and to the same powers. Okay, and so I'm not sure if that one has any. Yep, doesn't look like there are any. The next one is 3x. I think that there's another x term here with 9 and 0.34x. Okay, so what do these look like? Remember that the x looks like sticks. Okay, so here's our 3x. We have 3 sticks, positive, so I'll keep them open. 9.34x, which would be like 9 of these sticks. 3, 4, 5, 6, 7, 8, 9. And then part of a stick. Okay, that's the 0.34. Now, since they're all sticks and parts of sticks, we can combine them together. Okay, and so we get, we can combine them together like this. Okay, so they're all the same type of thing. Next one is, let's see if there's any x squareds. Any x squareds? Yes, x squared and 42x squared. Okay, are they all like each other? Yes. X squared, if you recall, was a square, side length x. Okay. 42x squareds there's 42 of them. So they can combine together. They are the same kind of pieces. And what we get is 43x squared. Okay. So those are done. And it doesn't look like there's any other types of things that are like each other. Okay. Like terms have to have the same variable and the same type of variable and to the same power. The order doesn't matter because it's all multiplied together, so it's commutative. What terms can be added or subtracted? Geometrically, you can add and subtract terms that have the same size and shape, that they are congruent. Algebraically, you can have the same, they need to have the same variables, all raised to the same power. Here's a few places where students go have misconceptions. Here's a case example. Daisy claimed that 3x and x cubed were like terms because they could be combined into 3x to the fourth. Okay, can we combine 3x and x cubed to 3x to the fourth? Okay, so that's what she's claiming. 3x plus x to the third equals x to the fourth. 3x to the fourth. So that's her question. Her reasoning is because we have the rule that says when the bases are the same, we can add the exponents. Okay, what do you guys think about that? So take a moment to pause the video and come up with an idea about why that's true and why that's not. Okay. Next is the rule is actually for multiplication. This is not true. If you have 3x times x to the third, then that's going to be 3x to the fourth. Yes, that's true. But notice that there's a big difference here. Comparing adding those two terms together and timesing those two terms together. Okay. This right here is true because 3x is this is the same as 3x times x times x times x. Okay, so x to the third is these three x's together multiplied together. 3 times x is 3x. And so all of them are multiplied together here. So that's why it's 3x to the fourth. Okay. So that answered that question down there. How would you explain or help her realize it? You can even go, let's go back. You can even draw pictures of this. 3x, remember that 3x as a picture, and that's what I would probably say is use the algebra tiles to show pictures. 3x is here are 3 of these squares, right? No, sorry, not 3 of the squares. We're going to have, not squares, they are actually, they're actually the sticks, the rods there. So 3x is 1, 2, 3. Now x cubed, we haven't really seen this manipulative, but it's actually like x cubed, where all sides are x's. Now, we can't combine these together at all through addition, because addition is multiplication here. We're not talking about groups of objects like multiplication, but addition here. So we can't combine them together. They'll just be 3x and x cubed, okay, since the objects are different. Okay. There's a debate about whether or not 3 times a times b squared and subtract and negative a b squared a are like terms. Person A argues that they are not, and person B argues that they are. So what do you guys think about that? Go ahead and pause the video and form an argument. Okay, so what do you guys think? 3ab squared. 3ab squared is 3ab squareds. Okay. Now what does ab squared look like? Now these are all multiplication. 3 times a times b times b. Okay, so let's draw a picture of one ab squared. Okay, this is going to be a, this will be b. I need to make the other dimension another b length. So a is kind of shorter, okay? B is kind of longer. So here's 3ab squared. There's one of them. There's two of them. Okay, short rectangle for the AB rectangle. Okay, long B depth for that one. Okay. Now, subtract AB squared, the minus AB squared, or B squared A, is negative B times A. Okay, so a picture would that be is going to be filled in, but here's going to be our B was kind of longer. B squared is right here, and then it's going to A depth, which is not very long. So it's B and A, which is shorter. Now, are these like each other? Okay, I'm going to fill that in because it's negative. It's going to be a red block. And it turns out that they are. Because notice that these B's right here, B times B dimension are down here. And then the A dimension is right here. Okay. So they are like terms. They have the same block picture. So when you combine them together, is equal to, and they're also commutative. They have the same picture, but they're also commutative. And meaning that we can also write minus b squared a is equal to minus ab squared. Okay. So if I have 3 ab squareds and I can combine these together, they make a zero pair. Okay, so then I actually end up with 2 ab squareds in the end. Hope thinks that r cubed and r cubed t are like terms. Person A argues that they are, and person not, then person A argues that they are. Okay, so let's draw a picture. Okay, r cubed is just a cube with all lengths r. R and R and R. Okay? All lengths are R. Now r cubed t is an r cubed, but times t, which means that there's a fourth dimension. R cubed raised to the t. Not raised to, r cubed multiplied by t. So it's a cube, but with another dimension of t, a t distance in another direction, but we don't have 4 directions. Okay, because of that, they're not like terms. Okay, they also have that different variables here. You can't commute this one to make this one. Okay, variables are different. Okay, so that's what we have for our lecture. Let me know if there's any questions.